Fantastic. Thank you, Rusty. So, hi, everyone. I'm William Smith, a professional services engineer with Jamf, and today we're going to be talking about finding trees in a forest. Almost 15 years ago, I was asked by a colleague, Diane, to join her team in starting a blog. And this was for her website about Microsoft Entourage. For those of you who aren't familiar with what Entourage was, it was the predecessor to today's Microsoft Outlook for Mac. We started the blog in 2007, and we maintained it for about 3 years as a source of tips, tricks, help, any kind of troubleshooting, all things Entourage. Then in 2010, we learned Microsoft would be releasing Microsoft Office for Mac 2011, and they would be replacing Entourage with Outlook. Well, there went the domain name. After some discussion, Diane and I decided to take the Entourage Help blog and turn it into a website that would be all about Office for Mac, including Excel, PowerPoint, and Word. We decided to call it officeformachelp.com. We worked for a couple of months on the design while waiting for Microsoft to release the new editions of Office, and we knew ahead of time what that date was going to be. But there was a problem, though. No one had ever heard of officeformachelp.com. It was an unknown website. Diane had spent nearly 7 years establishing the Entourage Help page website, and together we'd added content over the next 3 years. We didn't want to lose all that search traffic that Google Analytics said that we were getting when we changed over to a new domain name. Thanks to search engine optimization, at one point, it was a toss-up for the top Google search result between the Entourage Help blog and the HBO series Entourage. We asked our current hostmaster, is there anything that we can do about this? And he gave us a solution using regex. It was really simple, and it worked beautifully. The root of most every website contains a .htaccess file. This is a configuration file for Apache web servers, and it's quite often used to perform redirects. So, for example, if someone tries to access a page on your site using HTTP, a .htaccess file can redirect the page to HTTPS. Or if I wanted to redirect someone to my www page when someone just entered my domain name, .htaccess can handle that too. In our case, we used a rewrite rule that included not only the domain name, the change, but it also included code for something called a permanent redirect, which is 301. The 301 told Google, as well as the visiting browsers, always redirect to officeformachelp.com if ever you're coming to entourage.mvps.org. This is really where everything starts. We used a rewrite rule, and the regex made all of this work. So when we're looking at this, basically, whenever someone visits the blog on entourage.mvps.org, we told the browser, hey, we've moved to officeformachelp.com permanently, just start going there from now on. And to update Google searches, we simply had to submit a request online to have them rescan our site. So in just a few days, a search for any of the old content linked visitors to the new site. And if someone linked deep into the old site, the rewrite rule preserved the entire URL, and visitors were redirected to the same deep location on the new site. So what do all those backslashes, dollar signs, parentheses, and asterisks mean? That's what we're going to talk about today. For the first half of my presentation today, I'm going to cover the basics, including what is regex, characters with special meanings, and character classes and groupings. I don't have time to cover all the shorthand characters, but I'll cover a few, and I'll go over enough about regex to get you started using it. Then in the second half of my presentation, I'll talk about applications and command line tools that support regex. I'll give you some real world examples for using regex, and then I'll give you some really useful resources for learning more about regex and where to practice. So let's get started. What is regex? Regex is short for regular expression, which is a pretty confusing name. The word regular comes from the concept of a regular language, which is a computer science term. Basically, a set of symbols is called an alphabet, but an alphabet doesn't need to contain just letters. It can contain any set of symbols. So in this example, the alphabet contains the numbers 0 through 9, but notice all the way to the very end, it also contains a hyphen. Now, putting two or more symbols together forms a word. Here I have 6 examples. I've highlighted every other one just to make it a little bit easier to read. If you look at them closely, what kind of pattern do you see in these examples, these words? What are these words? Now, those of you from the United States, you should recognize these, but anyone else from outside the US, you may not. They're a list of 5-digit and 9-digit zip codes. A language is a subset of all possible words. The name of this language is United States Postal Service zip codes. For those of you outside the US, translate this to your own zip code structure. Or you might use another example like the structure of a telephone number. Each word in our example here contains either 5 digits or 9 digits separated by a hyphen. That means that there's only so many possible words in the US zip code language. A regular language can only contain a finite number of words. That means we can use an algorithm to determine whether a string of characters is really a word. The algorithm for the US zip codes is pretty simple. A valid word is either 5 digits or 5 digits followed by a hyphen, followed by 4 more digits. So so what we're effectively doing is looking for patterns in the strings of words that we're examining. Regular expressions, or regexes, or regexp, or regexen, are patterns. And when we use them, we're looking for matching patterns. So if regex is about pattern matching, what the heck is pattern matching? And what can I do with it? In a word, we use it for validation. Here's the subscription page for the New York Times. Today, your email address is your unique identifier, and it's required for a lot of online transactions like subscriptions. It has to be a valid email address, or the Times won't let you subscribe. How does the web developer know what you've typed is an email address? What if I type Jerry? Is that an email address? The page doesn't seem to like it. Or what if I put in a phone number instead of an email address? Does that work? No, it doesn't. But if I put in my email address, the page seems to be okay with that. Why? Is the New York Times really storing a database of every possible email address and comparing what I enter to that? Well, email addresses are limited to 320 characters, which is a very finite number, right? So what are the permutations of that? Given that the local part of the address, the part before the @ sign, is limited to 64 characters, and there's about 56 allowable characters, we just need to calculate 56 raised to the 64th power. That's pretty straightforward. Now, the domain part of the address, the part after the @ sign, has a higher limit of 255 characters, but about half the allowable characters at just 37. Again, we just need to calculate 37 raised to the 255th power, and for all practical purposes, that equals roughly infinity. Don't forget, we now need to calculate the potential of all those local parts of the addresses, the part before the @ sign, to the potential of all the domain parts of the address, the part after the @ sign, and congratulations, you just crashed the internet. Not only is creating a database of all possible email addresses impractical, it's practically impossible. Save the internet. Use regex. We can all tell just by looking at an email address that it's an email address, just like we can tell by looking at a phone number that it's a phone number, or by looking at a zip code that is probably a zip code. We're seeing patterns. If we look at this email address, it's easy to say the pattern. So tell me if you think this is right or wrong. An email address is a string of up to 64 characters, followed by an @ symbol, followed by a string of up to 255 characters, with at least one of those characters being a dot somewhere in the middle. All right, does that sound fair? Here's what the regex for that might look like. There could be several different types of this. This is one that I just happened to pick. And I'll be honest, it's easier to write a regex than it is to read what it does. As a favor to your future self and anyone else reading your regexes, try to include documentation that explains what you're matching. You'll thank yourself later, and so will others. So let's break this down. We haven't yet covered any regex symbols or shortcuts, but we'll be doing that shortly. For now, I'm going to step you through this one. To read a regex, start at the left and identify what you can. To make this somewhat easier to read, I'm going to color code all the regex symbols. And anything that's in white is just going to be a literal character like A, B, C, or 1, 2, 3. The first item, /W, is a regex shortcut. It means any single character, any single word character, or literally any single character in the list of lowercase letters, uppercase letters, and numbers. So lowercase, uppercase, numbers. You might notice this shortcut is appearing a couple more times. So long as you see the shortcut by itself, it means just one character. But here it's followed by curly braces with numbers in them. This signals something called an occurrence indicator or repetition operator, which are just fancy names meaning that the character before it is going to repeat. That means I may have just one character or up to 64 characters. That's what those numbers mean. So think about your own email address and the part of it before the @ sign. Would your email address fit this pattern? For some of you it will, but for others it won't. If your email address is in the form of first.last, you'll match the letters, but the /W matches only letters and numbers. It doesn't match the dot. Keep in mind, this regex may be just fine for some of you because you may know that your company's email address language doesn't include dots in the username. But for the rest of you, you'll need to ensure your regex accounts not just for letters and numbers, but also a dot, and maybe even other characters. As you learn regex, you're going to create patterns that work for you, but may not work for someone else. Don't be too concerned, but do be aware that it may need to match more than what you previously thought. Again, you'll see there are two sets of curly braces with a range of numbers following the /W character. These are defining the domain, which must have a period between the domain name and the top level domain like .com, .edu. Currently, the longest top level domain is only 24 characters, but nothing says it can't be longer. And currently, the shortest top level domains are just 2 characters like US or IN. Finally, here's our @ symbol and our period in white. The @ symbol looks normal, but what's with that backslash in front of the period? In regex, the @ symbol has no special meaning like it would in an email address. @ is just @, nothing more exciting than that. But a period in regex does have a special meaning. We'll talk about that in just a little bit. For now, if we want to denote a literal period, we have to precede it with a backslash, which is called an escape. If you've done any scripting, you've probably already put in some escapes into some of your work. Here's an example where our script may require that we put double quotes around the entire argument, which is display dialog, hello world, buttons, okay. But if we read that literally, we get a fragmented set of arguments, which are some words or characters are in double quotes, but others aren't. What we need to do is use double quotes at the beginning and the end to keep the entire argument together. And then we need to escape the inner double quotes to indicate that we literally mean just double quotes. There's about a dozen or so special characters like that period that'll need escaping. if we want to use them literally and not as special regex characters. That's the short explanation of regex. We're using it to validate whether a string of characters matches a pattern like an email address, a phone number, or a zip code. If we validate text, we can find errors and correct for them. It's much easier to look for a pattern than to try to create it. Understand that every possible permutation of a word is not necessarily possible to store. Next, let's look at the different types of characters that can make up regex. Now, before we get started, I'd like to point you to one of my favorite online tools, regex101.com. I'm getting ready to show you a lot of examples, and if you find anything interesting, you can experiment with it here. The top field is where you'll enter the regex, and the bottom field is where you can type in one or several test strings to see if the regex is going to match. The letters in your test strings will highlight as you complete the regexes, and if the regex doesn't validate the test string, it simply won't highlight. So open your browser and play at home if you like. First, I'd like to say there is no shame in making a regex cheat sheet. In fact, I encourage it. So let's start one here, and on the right, we'll fill it in as we go. Now, in regex, letters and numbers match themselves, and specifically lowercase letters only match lowercase letters, and uppercase letters only match uppercase letters. If we look at the middle section, the word moon, all lowercase, matches moon, all lowercase, and the word moon with a capital M matches moon with a capital M. The word moon, all lowercase, though, is not the same as the word moon that begins with a capital M. This doesn't validate. Likewise, the string 456 doesn't match the string 564, and therefore it doesn't validate either. And looking at the last example, Penn space state doesn't match Penn State without a space. All right. So hopefully it's simple enough to get started. Next, a period matches exactly one character. If you hear me say dot, I still mean a period. I sometimes use those terms interchangeably. It can match any lowercase letter, any uppercase letter, a number, a symbol, a space, anything. Note in the second moon example where the regex is capital M dot dot N, the two periods mean exactly two characters, whether they're letters, numbers, symbols, or even a space. And for the two Penn State examples at the bottom, the regex is Penn dot space. That means it'll match Penn State with a space in the middle, but it still won't match Penn State with no space. A dot means there must be a character. All right, before we get into this one, I'd like to point out that in our cheat sheet on the right, I've added both the period to mean a single character, and I've added the backslash period to mean a literal period. If I were creating a regex to validate an IP address, for example, I'd use a backslash period to ensure we're matching the dots between each octet. Moving on to square brackets now. These indicate a character class, or better yet, a character set. When you see square brackets, you have a choice of any one character inside, lowercase a, or b, or c, or uppercase X, or Y, or Z, or number 1, or 2, or 3. When you add the caret symbol to the beginning of the list, that means not. You might also hear the caret symbol referred to as the hat symbol, HAT. In these examples, it means not vowels or anything but vowels, not RSTLNE or anything but RSTLNE, and not even numbers or anything but even numbers. Say this to yourself in your head in any way that you like to help you remember what that caret means or that hat. In the first example here, your choices are upper and lowercase letters A, B, and C, but just one of those though. Look at the second example with the word dog in brackets. Can you tell me why it doesn't match dog the word? Because you can only match one character. It'll match uppercase D or lowercase o or lowercase g, but not all three. And in the last example, we have a regex that matches 4 different versions of dog. Remember, an uppercase letter by itself matches itself. So capital D by either a capital or lowercase o, followed by either a capital or lowercase g, will match dog, but it won't match any version of dog that begins with a lowercase d. We're not limited to individual characters within square brackets. We can actually specify a range of letters or numbers to keep our character set short. Lowercase a through z, uppercase A through Z, and numbers 0 through 9. And our ranges can be just partial ranges. If we want to exclude the letters A through E using the caret symbol at the beginning of the set, we can do that. And notice we can specify multiple ranges like not L through P and not X through Z. This regex still matches just one character, but just not any of those capital letters. And don't be fooled if you see a character set that seems to have a large range, like 1 through 489. Remember, we're matching just one character from inside the square brackets. This is really 1 through 4, or 8, or 9. Last, we can mix alpha ranges with numerical ranges and single characters too, as we can see in the first regex here. A match must start with capital A, B, or C, or number 1 or 2 or 3. The period at the end matches any character. So be sure not to mix up your ranges though. There's no such range as a lowercase a through a capital Z, and there's no such range as a letter through a number. That makes no sense if you think about it. Like the period, the following characters are special in regex, and it's easy to get them confused. I've put them all together here because they all kind of behave in the same way. They modify the preceding character in some way. When an asterisk follows a character, it repeats that character 0 or more times. So for example, if you ever see the letter Q followed by an asterisk, the regex is going to match a single Q, 2 Qs, 3 Qs, 50 Qs, or no Qs at all. An asterisk matches 0 or more times. The plus symbol does almost exactly the same thing as the asterisk, except that it must match at least one time. So 1, 2, or 50 Qs, but there has to be at least one. If curly braces with a number follow a character, that means match this character exactly this number of times. If curly braces with 2 numbers separated by a comma follow a character, the regex will match any repetitions from the smaller to the higher number. In this case, it matches 2 Qs or 3 Qs or 4. No more, no less. And then finally, if a question mark follows a character, that means the preceding character is optional. If it's in our pattern, that's great. If not, no big deal. So what are some examples using these characters? Here we've got a few. An asterisk indicates 0 or more repetitions. The first regex will match something that looks like a phone number, something that looks like a sports score, something that looks like a negative number, or just a hyphen. The second example is really interesting, and you're going to see this used a lot in regex. Remember, the period indicates a single character, but when it's followed by an asterisk, that effectively means match any length string you want, from 0 characters to a sentence to something larger. Be on the lookout for this one. You're going to see it a lot. The last example might be a version number. Every match will begin with 16.1. We're escaping the period because we literally mean a period is the next character, not one of those special regex characters. Then the string is followed by 7 or 8 or 9, followed by 0 or more characters. Remember, those characters can be numbers, letters, symbols, or spaces. Now, if we want to be specific about the number of matches, we just need to put a number in curly braces. So here we have the Darth Vader no regex with 12 O's. In the second example, I'm throwing in something new, the \D shortcut. Earlier, we saw the /W shortcut, which stood for any letter or number. \D stands for only number 0 through 9. If I want to specifically match a phone number, my regex must match these digits. That's where the D comes from, or a hyphen and 4 digits after that. Now here, the curly braces follow a hyphen and possible matches that will include at least 2 and up to 6 hyphens. So a range of 2 to 6 hyphens. And finally, there can be humor in regex. It may not be funny to everyone, but it's there. A question mark means optional. While some of us may disagree on the spelling of the word color with the optional letter U, regex can remain neutral and accommodate everyone. And where some folks like to say aluminium, while others say aluminum, regex will always say it correctly. Now that I've introduced you to the digit shortcut, I've added that to this cheat sheet along with its counterpart, \D, and that matches any non-digit character. There are a lot of these / shortcuts, too many to cover today, but knowing just a handful here that I'm showing you is going to go a long way to accomplishing anything that you want to try to do. The last 2 items that I'll cover before we look at some examples are capture groups and the alternation or operator. Until now, I've been telling you that we're matching just one character at a time. But what if you wanted to match multiple characters? Parentheses around 2 or more characters make a group, and that group will be taken in whole. By themselves, they're not very interesting because something like ABC in a group is the same as ABC without the parentheses. But combine capture groups with regex special characters, as you see in the second example, and you can do some pretty interesting things. For example, you can find numbered files that may or may not begin with IMG. Here, the entire IMG string is optional, not just each letter. Or in the third example, we can use regex to complete Old MacDonald Had a Farm. E-I-E-I-O. Now, let's talk about the alternation character, the vertical bar or pipe symbol, which we all know as just or. It's really useful in capture groups, and it lets us choose one string from the group and treat it as a unit. In the first group, we have a choice of ABC or 1, 2, 3. When we put it in context with the other characters, we can match multiple strings like moon or mean without having to explicitly write out moon or mean. And we can even nest groups within groups. Now, in the third example, we have a capture group of 0 or 1 inside another capture group that begins with 1, and then we say repeat it 2 times. All right, what does that mean? That gives us 4 possible matches: 10, 10, 10, 11, 11, 10, or 11, 11. All right, if this seems confusing, it can be. As I said earlier, it's easier to write a regex to meet your own needs than it is to try to read somebody else's. But let's take a stab at it. Let's try writing some. We have a full cheat sheet on the right, but it's by no means exhaustive of the characters that you're ever going to be able to use in regex. However, these few conventions and shortcuts will be enough for what we need here. The best way to learn regex is to practice, so let's build a few. If you're using the regex101.com site that I showed you earlier, enter the examples that I give you here for testing, and then start building your regex in the top field. Here's a list of model identifiers for MacBook Airs that support macOS Catalina. What would a regex like that look like? I'll give you a few seconds to think about it. The first thing that I would do is start at the left to try to find all the leading characters that each string has in common. That's pretty easy. Each string begins with MacBook Air. The next character in each string is a single number, but they're not all the same. However, they are in a range of 5 to 8. So I use square brackets to define that range. Next, in all the strings is a comma. When it's by itself and not in any brackets or braces, it's just a comma. And each string ends with a number, either 1 or 2. I could write it this way using square brackets, or I could even write it this way using parentheses as a capture group. Both work. There's really no right or wrong other than I'm trying to write as efficient a regex as possible, and that usually means shorter. I like the top one better. We'll take a look at more model identifiers in just a little bit. Here's a list of Class A IP addresses, and I need to match any IP address on these networks. And let's assume that we have a simple subnet mask of 255.255.255.0. What would a regex for this look like? I'll give you a few seconds to think about it. Starting at the left to find all the leading characters that each string has in common, we'll start our regex with 10\dot. I want a literal period, not a special regex match anything period. The second octet is either 11 or 20, so I'll use a capturing group for that. After that, all the addresses continue with .0. Again, I'm escaping the periods because I want a literal period. And then I need to match any IP address on these networks. So the digit character with a range of 1 to 3 digits works just fine. Now think about this regex for the last octet for a moment. What's it really going to match? It'll actually match 000 through 999. But octets and IP addresses only go to 255. Is that a problem? Well, it depends on what you're trying to accomplish. If I'm using this regex to validate a form field that somebody's filling out online, I probably need to be a lot more careful that the last octet doesn't go past 255. But if another system is simply feeding me a list of IP addresses that it generated, and I'm simply matching those, then I don't need to worry. It's the other system's responsibility to make sure that it's feeding me a valid IP address. I'm simply making sure that it's in the right network. This is one of those situations where sometimes a simpler regex is good enough. Here are some Microsoft Office 2019 version numbers starting at 16.17. For the next 2 to 3 years, these will count up to 16.52. Microsoft Office 2022's starting version number will be 16.53. So my goal is to identify any Office 2019 version. And notice that I have a few of these that have .1 updates too. What would a regex like that range look for? 16.17 through 16.52, with possibly some additional numbers at the end of some of those. I'll give you a few seconds to think about that. It starts off easy with matching 16 dot. But now we have to match 17, 18, and 19, and they all begin with 1. We also have to consider, though, the numbers in the 20s, the numbers in the 30s, the numbers in the 40s, and a few numbers in the 50s, and then stop. So it's a range of 17 through 52. How do we do that? We break up those numbers into groups. So to start a group, we add an open parenthesis. To start the group, I'm interested only in those minor versions, those minor version numbers that won't use a full range of numbers like 0 through 9. So I'm looking very specifically at 17, 18, and 19. I can match the number 1 in all of those and use a range for 7 through 9. That lets me match versions 16.17, 16.18, and 16.19. Now, I'm thinking about the next range for the 16.20s, the 16.30s, and the 16.40s. I can handle those using 2 sets of square brackets. The first brackets match the 20s, 30s, and 40s. The second brackets match 0 through 9. Now that gives me a range of 20 through 49. Lastly, I need to match 50, 51, and 52. And I'll do it the same way that I match 17, 18, and 19. I can match the number 5 in 16.52 literally, and then use square brackets to create a range of 0 through 2. Now I close my capturing group, and this gives me 3 possible matches: 17 through 19, 20 through 49, or 50 through 52. And as far as those version number strings that have the .1 at the end, the smaller update, I can handle that with a .* to match 0 or more characters at the end. If there's a .1 or a .2 or whatever, great. If not, no big deal. All right, that was a lot of detailed information thrown at you pretty quickly. But just like we had to learn the letters of the alphabet before we could make words, we need to learn at least a few regex symbols and shortcuts to make words in regex. The difference, though, between learning our ABCs and regex is that learning more symbols and shortcuts will actually allow us to write shorter regex strings, not longer. Anything that's shorter is going to be easier to read and understand. Now, let's take a quick look at where you can use regex. I'll show you a few applications and command line tools that support it. I give BBEdit from the folks at Barebones Software a lot of love because I love their product. It's a very powerful plain text editing application with a very simple interface. I use it to write my test scripts and to write and test my scripts, edit XML and JSON files, and sort and massage all kinds of information. And even though it's been around for nearly 30 years, version 1 was released back in 1992, and now it's up to version 13, it still doesn't suck. Its find replace feature includes an option to use regex. It's called grep. Now, some of you who've done any scripting might be thinking, where have I heard that before? You've likely used it in many of your scripts to grep for something. Maybe you've used cat to read a file and then pipe that into grep to find all the lines that include the word dog. And by the way, for those of you who are familiar with the useless use of cat here in this command, I did that on purpose. For the rest of you who don't understand what I'm talking about, I'll explain what I mean by that just a little bit later. The name grep comes from global regular expression print, or more understandably, globally search for a regular expression and then print just the matching lines. What you may not have realized is that the RE in grep actually stands for regular expression. That's a high likelihood. There's a high likelihood that you've actually been using regular expressions all this time and maybe not even realized it. Don't worry if you're new to regex or if you're just now digging into regex, because BBEdit includes these 2 handy buttons. Clicking the first one reveals a menu of built-in patterns, which you can edit to add your own patterns. It'll fill in the regexes for both the find and the replace strings. All you have to do is supply the document. And if you need some help with some of the characters when making your own regexes, clicking the help button reveals BBEdit's own cheat sheet with far more examples than I included in mine. One of the interesting things you can do with regex in BBEdit, or most any application that supports regex and find replace, is take a pattern like this and run it against a bunch of text, like you see there in the background. This is the famous Steve Jobs quote. That's debatable if it's Steve Jobs or somebody else from their Think Different commercials. Here's to the crazy ones. And when you do run this regex against it, it'll actually help you find double words that you can't easily see when reading through the text. The \1 you see in the replace field is actually a shortcut referencing back to the captured group in the parentheses in the find field. This search is effectively saying find all doubled words and replace them with single words. Another application that many of you know is Jamf Pro, which is a management system for Apple devices. It has two features, smart groups and advanced searches, that allow an administrator to search inventory using any of about 200 pieces of information collected about a device. Here, I'm using criteria to match the model identifiers of all Macs that support macOS Catalina to create a smart group. Now, can any of you think in your head how many specific models of Mac actually support Catalina? As of May 2020, Catalina will run on 62 models of Macs. And the only way we have to identify them in inventory is to use their model identifiers. We can't take Apple's term of MacBook Pro 13-inch 2020, 2 Thunderbolt 3 ports, because that name doesn't exist anywhere on the Mac where we can read it from the operating system. Even if it did, we'd still have to match 61 more of these names. So more importantly, model identifiers follow a pattern. It's longer than any regex we've seen so far, and I've made liberal use of ranges and capture groups, but this one regular expression will match these 62 model identifiers. And in Jamf Pro, I get to simplify 62 different criteria separated by ORs to just one regex. And processing this regex, even with 8 OR operators in the string, is going to be a lot more efficient than processing 62 possible matches. If you'd like to experiment with this and deconstruct the regex, I'll have it along with the list of model identifiers in the resources at the end of the presentation. If we have a file that lists all Catalina compatible Macs by their model identifiers, grep can read that file and identify every line that contains the pattern Pro. I have them listed in 5 columns here, but pretend they're each written to a single line in the file. And notice this time, I'm not using cat to read the file and piping that into grep. I don't need to. Grep is perfectly capable of reading its own files. That's what I meant earlier about the useless use of cat. When I run the command on the file, it prints only these lines that match my pattern. And from here, I can take the new list and process it however I need. I can further narrow my list using brackets in the command to just find newer Pro models like those 12 through 16. But what just happened? I lost all my Mac Pros and my iMac Pro because their model identifiers aren't in that range of 12 through 16. All I'm left with are just MacBook Pros. All right, that should be easy to fix. I can adjust my regex to add a capture group in parentheses to find numbers in the range of 12 through 16 or just a single digit. And it'll look something like this. But for some reason, when I run the command, it doesn't work. I get nothing matched. Why is that? If we need to get more complex with our searches, we need to add the -e option, which is the shorter form of -- extended regexp. Both of these commands are the same. One is just a shorter way of writing it. I encourage you to use the longer form in your scripts because it better explains to yourself later or someone else reading your script what your script is actually doing. But for the time being in the terminal, just abbreviate, use the shorter version. So what's an extended regular expression? Simply put, anytime that we need to use certain regex characters like the plus symbol, the question mark, the pipe symbol, or the parenthesis, we're no longer performing a basic pattern match where our regex characters must just match one character, like just the number 1. We're now performing a more complex match where our regex characters may match more than one character, 1 or 1 1 or 1 1 1 or 1 1 1 1. That's extended. Here's our grep command that didn't return anything. We'll add the -e, and now when we run it, we get all the Mac Pros, including the iMac Pro, the MacBooks Pro, and the Macs Pro. One last note for you about grep. Grep-e is the same as egrep. The E in egrep stands for extended. Another common tool we use in our scripting is awk, and it too supports regex in several different ways. I'll show you 2. One of the most common uses for awk is to evaluate text files with multiple columns of text. Here, I have the contents of a comma-separated list, values list, a CSV file. The Mac serial numbers with Mac serial numbers in the first column, model identifiers in the second column, and departments in the third column. I'm only showing you 10 rows here, but imagine this could be a list of hundreds or thousands of computers. My goal using awk is to identify all the older MacBook Pro models my company no longer supports, and then contact the managers of each department to schedule refreshes. Specifically, the MacBook Pro models I want to refresh are those with an identifier of 10 something or less. I'll start with a simple awk statement that gets the last column of data. The -f lets me specify a character that separates each column. In this case, it's a comma. And the print $4 means print the 4th column. Notice the model identifiers themselves add an extra comma. That's why I can't use $3 to get the departments. I have to shift over to $4. So when I run my command on the CSV file, it returns just a list of my departments, the 4th field. Now, I need to add some more awk syntax to handle the regex. I'm doing multiple things here. First, I'm using $2 to tell awk search in the second column with all the model identifiers. The regex is between the 2 slashes, and it looks something like, and it's looking for the string MacBook Pro 1, followed by a range of 1 to 9. So it matches all MacBook Pro model identifiers, 11 through 19. The highest number to date is on the first line, which is 16. So this regex is going to be a little bit future-proof for years to come. And then finally, I don't want to match identifiers 11 through 19. I actually want everything else. So when using regex and awk, the tilde means matches. By putting a bang or an exclamation point in front of that, that means don't match. Altogether, my awk command is saying, read the file at the end of the command, which is assetslist.csv, divide the text of the file into columns at every comma, read the second column of each line and look for anything that doesn't match MacBook Pro 11 through 19, and then print out the 4th column. What I'm left with are these departments. And if I wanted, I could add a sort command to the end to alphabetize and remove duplicates so that all I get is just customer service, marketing, sales. Now, here's another way to use regex and awk. There's a command you can run in terminal called uptime, and it does pretty much what it says. It tells you how long your computer has been up. And if you look at the result here, it's pretty easy to see that my Mac has been up 4 days, 10 hours. That could be handy for reporting purposes and for troubleshooting. But there's a catch to this response that you're going to see. When working with one of my customers, we created a command to get the uptime, and then we trimmed out the parts before and after it that really weren't important to us, just to give us the uptime string. But we kept getting really inconsistent results, and eventually we found out why. The result of uptime could be in one of 5 different string formats, like you see here. So looking from top to bottom in this list, the computer could be up a certain number of days and minutes, or it could be up a certain number of days and less than 2 minutes, or it could be up a certain number of seconds, or less than 60 seconds, or less than 2 minutes. So then we had to think about, how do we divide up this information? Commas are usually a pretty good bet, but in this case, the first two results actually include commas as part of the uptime. The rest don't, though. We also considered spaces, but again, the first two results contain spaces too. Then we thought about using strings of characters before and after the uptime, and that partially worked. But we couldn't always guarantee 2 users would be logged in. There could be more. So regex helped us with this. Now remember, the -F specifies a field separator. That lets us divide rows of text into columns. And then in our solution, the word up with a space after it defined our first field separator. And then we used the OR operator to specify a second operator that began with comma, followed by a number range, followed by the word users. This let us capture uptimes whether they contained commas, spaces, or not. One more very simple example. If you're familiar with grep and awk, then sed can't be too far behind. The vast majority of the time that we're using sed, we're trying to remove something or change something. A lot of us like to follow a computer naming convention in one form or another. One of the reasons is for compatibility maybe with external systems, but sometimes those systems don't like special characters, but the macOS Setup Assistant frequently names our computers something like this. We can use regex in a sed command to remove all alphanumeric characters. Here, the sed statement is substituting any character that's not a number or an uppercase letter or a lowercase letter with nothing. So the result is pretty straightforward. All symbols and spaces get removed. All right, I hope by now you realize that regex has probably been a part of your scripting command line work, whether you knew it or not. If you weren't aware, I hope you take away today that you've got a powerful search and editing tool baked in to a lot of your existing daily tools. What I'd like to do now is show you a couple of more interesting uses that I've helped put together for some of my customers. Maybe these will give you some ideas for where you can start using some regex. I had a customer with 472 Macs enrolled into Jamf Pro. This was a system that he largely inherited from the former administrator who left the company, and he wanted to change the computer naming scheme to something slightly different from his predecessor. On top of that, he had some developers with admin rights who liked to change the computer names on their own to something completely different. And then sometimes the technicians who were preparing the Macs for the end users forgot to rename them. The old naming scheme followed a very simple convention of 3-character site code, -Mac, and then the last 5 characters of the computer serial number. Now, if you know anything about the structure of Mac serial numbers, you know the last 4 characters identify the model of the Mac. They're going to be the same across many different Macs. So these are some of the names that you could expect to find on his network. The somewhat properly named naming convention, or maybe Prometheus for a developer, or maybe Admins MacBook Pro when somebody forgot to rename the Mac. What he wanted to do was name everything similar to the established naming convention, but instead of using the part of the serial number, he'd run a script at the enrollment that prompted technicians to choose a site and enter the asset tag from the bottom of the computer. The script was easy to put together, but what we had to do next was identify the Macs that didn't follow the new naming convention. So to identify Macs that were named correctly, as well as incorrectly, we created 3 smart groups and we put them on our dashboard to track our progress. The first smart group used regex to identify Macs with the older naming convention where the site code was one of 8 possible 3-letter sites, -Mac, and then the last 5 characters of the serial number. Knowing Apple's format for serial numbers, we knew that the last 5 characters would contain a combination of letters and numbers, or digits. The second smart group's regex identified Macs with the new naming convention that we wanted. Instead of 5 alphanumeric characters at the end, we wanted the asset tag of only 5 numbers or digits. And then we added a third smart group to identify Macs with names that didn't match either one of these patterns. When we went to look at the numbers, we found something odd though. Our first group matched 420 Macs. Now we knew this would be the biggest group, so that kind of made sense. Our second group matched 20 Macs. That made sense too, because the technicians had been following the new naming convention for a few weeks. And our third group matched 32 Macs, where the names had either been changed by developers or the technicians had simply forgotten to rename them. All of these numbers made sense until we looked at our total Mac count, which was 452. We had a discrepancy of about 20 Macs. So if you look at this, can you see what we did wrong? I'll give you a couple of seconds to look things over. If you compare the regexes at the ends of both patterns, you'll see that the first matches any combination of letters and numbers, and the second only matches numbers. The same Macs that matched only numbers at the very end were also being matched by both regexes, not just the second one. So everything that was included in the Smart Computer Group 2 was also included in Smart Computer Group 1. What we had to do was modify the first regex to match only if there were both letters and numbers. The change we made was a little bit tricky. If you recall from our cheat sheet, the \W equals any letter or number, and the asterisk makes that 0 or more letters or numbers. So with the \W at both the beginning and the end of the regex, we guarantee the first and the last characters will be either letters or numbers. And then with the A through Z range in the middle, we guarantee at least one letter will be in that string somewhere. When we viewed our totals again, everything came out correctly. This was a good example to illustrate that if you're creating regexes to identify two completely different groups, be sure there's no potential overlap. Finally, here's one last project in regex that took me a while to complete. I've had more than one customer with a very specific need. They want to control the versions of software installed in their Macs, but they only want to enforce a minimum version. And here's what I mean by that. Let's assume that an organization deploys Microsoft Office and the version that IT deploys to production is 16.37. That's the current version today. This is their baseline, and some Macs are at baseline. That's good. They know that some of their users are on Insider Fast and may be on a later version like 16.39, and they want to leave those folks alone. They don't want to downgrade them. However, they have some users who are on older versions and falling below baseline, and what they need to do is upgrade these without touching them or downgrading anybody else. It sounds simple, right? It's as easy as saying update all Macs to 16.37 or higher. Such simple words. I thought it would be easy too. We could look at this two ways. I could either identify Macs where the Microsoft Office version number was greater than or equal to 16.37, or I could identify Macs where Microsoft Office was less than 16.37. I like to identify the state of Macs as they exist, not as they don't exist. That's a double negative. It doesn't make sense. So I chose to find all Macs greater than or equal to 16.37. Now, I'm working in Jamf Pro, and it's easy to see the version number for any application. We collect that information natively. However, there's a gotcha. Jamf Pro's ability to match a version number is there using the is operator, and it can do something like a wildcard with the like operator, but there's no ability to say greater than or equal to or greater than, and there's a reason why. Software version numbers aren't really numbers. They're strings, and strings of characters don't have a greater than, less than equivalent, at least not in the computer world. You and I and any computer can tell that 16.37 is less than 16.38 because they're both legitimate numbers. They're real numbers. But a computer can't do a greater than, less than comparison between an actual number and then something that looks like a number but is really a string. When I tell that to my customers, they look at me weird and they say, but of course it's a number. And I reply, when did any number ever contain 2 or more decimal places? It doesn't exist. And then I start showing them other applications that they're using where the version strings get really wild. For the most part, Microsoft Office's version strings contain 1 period, but there are hotfix versions where they'll tack on a .1 or something like that at the end, and they turn that into a string now. And look at Google Chrome and Adobe Acrobat. They each have 3 decimals. And Zoom at the bottom. Oh, Zoom. Needless to say, most developers don't follow a standard with regard to their version numbers. Office, Firefox, Photoshop, and Defender in this list appear to be following something called semantic versioning, which is 3 sequences of numbers separated by periods to denote major, minor, and patch numbers. Acrobat, at first glance, looks like it's following semantic versioning too, until you see that it includes leading zeros in the middle sequence in the version string. So is 006 the same thing as just 6? Who's to say? So regex to the rescue, right? Very much so. But when you try to do something that sounds as simple as equal to or greater than a version string, it actually gets a lot hairier. Let's take Google Chrome's version string. Where do we start? At the beginning or the end? At first, I started at the end. It's easy enough to change the 7 to a range of 7 to 9. That's already 2 possible higher versions right there. But then what happens if the 1 before the 7 increases? It goes up to 2 or higher. That means I change it to a range of 2 through 9, right? Well, not so fast, because now this won't match 117, which was the original number, or 118 or 119. So I'll solve that with a capture group and an OR operator. But if I do that, the 2 through 9 and the 7 through 9 only match 1 character. I've lost a number somewhere. So I can fix that by adding a \d, a digit, to the end of the 2 through 9 range to indicate 1 more digit. But that's still not right. I'm still missing a number if I'm going to match just the 7 through 9 at the end. So all I need to do here is just add the 1 back in front of it. All right, that takes care of the last 2 numbers, 1 and 7. We're accounting for whether the ending number 7 increases, and we're accounting for the 1 in front of the 7 if it increases. Well, I went with that for a while, and it was tedious. I also realized something else. If I went back to the original string that ended in 117, what's to say Google will stick with just 3 characters at the end? What if that 117 were 999? It could roll over to 1,000 or 10,000 or 100,000. So another part of my regex would have to account for that. I had to include the possibility that the last sequence would be 4 or more digits. Here's something new with those repetition braces. If I specify a minimum number of characters, but I don't specify a maximum number, that's the equivalent to 4 characters or higher. So I have to make sure that I include something like this for each sequence of numbers between the periods in the regex that I'm building. And what about the periods? I need to make sure I escape each of those because periods are special regex characters that match any single character. I want them to be just periods. So I hope you get the point that not only was this tedious, there were a lot of gotchas that I had to account for. The regex to match this version string or higher turned out to be a lot more than I had anticipated, and I eventually changed my tactic to start at the very beginning of the version string instead of the end, and that made things a lot easier. Here it is. This is a very complete regex, but it's not really that complex. You may notice that there's a lot of OR separators in this pattern. That's because this is just a bunch of shorter regex patterns strung together, and each one accounts for a possibility that I mentioned earlier, such as the number of characters in a sequence changing from 2 to 3 or 3 to 4. And if you look at this very first pattern, you'll see it accounts for the 79 at the beginning of the version string, growing from 2 digits to 3 digits or more. And then I added a dot star to the end to match everything else. It also accounts for each number in each sequence incrementing, such as from 6 to 7 or higher, or 7 to 8 and higher. All I had to do was work my way from left to right, and I found that for each sequence of numbers or each number, there was only one of 4 possibilities. I had found a formula for creating these patterns. And once you know a formula, you can automate it. So I spent some time and I wrote a script to create a regex for this very specific purpose of matching a specific version number or higher. It'll take most any version string that you give it. This one is for Google Chrome. This one is for Microsoft Office. You're going to see it's a lot shorter. This one's for Adobe Acrobat Reader, and you'll notice that I'm giving you a warning about this regex because the middle sequence in the version string contains leading zeros. Is that a 6 or a .006? We have no idea what this developer is doing. And finally, Zoom. With its spaces and parentheses in its version number, oh, Zoom, what were you thinking? The world may never know. I have updated my script to account for version strings with non-standard characters like Zoom includes, but again, I show a warning because when developers don't follow standards, we can't design patterns or scripts that will make them standard. So use with caution. The link to the script is at the bottom, but I'll include that in the resources at the end as well. Those were a couple of examples for using regex in the real world, and the regex version script is extreme. It's a little bit of a warning, but it's also a little bit of a consolation too, that not all regex patterns will be short and sweet. The more complex the string we need to match, the longer the pattern will likely get. So I'll reiterate what I've said a couple of times already. It's far easier to write a regex than to read someone else's regex. But look for characters and shortcuts that you recognize and look up those that you don't. It's like looking up a word in a dictionary. It makes sense once you know the definition. And now here's a quick list of resources to help you with building regexes. If this is your first journey into regex, or if you want to solidify and expand what you know, go to regex1.com. Each lesson here takes about 5 to 10 minutes and concentrates on a specific concept like the \D and the \W shortcuts, or ranges, or capture groups. If I've gotten you interested in regex, this is the next place for you to go. It makes learning regex fun. This is regex1.com. Once you've learned the basics from regex 1, regular expressions info is a great resource for detailed and more extensive uses of regex. Now, while I don't recommend it, because the site's really optimized for online use, you can download a 400-page PDF with all the content here. There's even a list of book reviews for regex books like O'Reilly's Mastering Regular Expressions. Don't let that publication date throw you off. Even though it was first published in 2002 and later updated in 2006, regex hasn't really changed that much in the meantime. The content is still as relevant today as it was 15 years ago. In fact, you probably have a hard time finding something that's newer that's not already covered in these older books. I've mentioned a couple of times regex 101, which lets you test your regex patterns and experiment. The explanations to the right are useful when you're trying to understand why something does or doesn't work. You're going to find dozens of these sites for regex validation. This one just happens to have an interface that I find easy to use. And this is regex101.com. And finally, if you want to practice your regex and have fun at the same time, nerdy fun, head over to regexcrossword.com. They have dozens of crosswords across several themes like cities. So if you understand the clue, then you're on your way to solving the puzzle. If you don't understand the clue, you've got regex to help you along. Remember, regex is about understanding the language of something like an email address, a phone number, or a zip code. The words that make up these languages are structured, which makes them regular. And if they follow a convention for putting characters together to make words, then we can identify patterns. It's the ability to identify patterns that lets us validate whether words are part of a language. Patterns in a regex are made of literal characters as well as some special characters. Sometimes a character in a pattern matches a single character. That's in the string that we're evaluating. That's a very basic regex. And then sometimes the special characters and sets and groups in a pattern can match multiple characters in the string. That's an extended regex. You may not have realized it, but you've probably been using some tools for a long time that include regex support, especially the grep command, which in itself is about regular expressions. I've shown you many examples from my real-world experiences using regex, and I hope they give you some idea for how you can use it in your world. The web is full of resources for you to learn and understand it. Regex isn't the new kid on the block, but it could become your new best friend when having to solve problems with data. Here's a link to the resources that I mentioned today. I'll have the slides and the files posted there shortly. Let's see if you have any questions.
Fantastic. Great presentation. We have two Q&A right now. One is a comment and another's a question. I'll start with the comment. There's an old joke. Programmer 1, I have a problem that I'm trying to solve with regex. Programmer 2, well, now you have two problems. There we go.
That's great. That's great. Bravo to whoever said that.
The second one is software version strings, or are software version strings the reason we don't see supplemental updates in Jamf's patch management?
Oh, good question. Fair warning, even though I do work for Jamf, I'm not part of that department. But I'm going to say I don't know, to be honest. And the reason I'm going to say that is because the patch management feature in Jamf Pro has its drawbacks. For the longest time, it was promised even well before I became a Jamf. And I'll be critical of our own product. I'm fair about that. It does have some drawbacks where we have to maintain those patch versions for you and those application title versions for you, unless you're going to also include your own patch reporting server. But in my fair assessment, and again, this is not to diss my company or anything like that, it is an area that could use improvement. And one of those things is exactly what you're talking about. How can we accommodate some of these odd strings? And again, how can we build in maybe greater than, less than? If we can do it with regex, maybe we can do it in Jamf Pro as well. But those are discussions really that are not part of my purview. They have to do with the product managers. I encourage you, though, go search on Jamf Nation, look for feature requests that ask for things like this. Things like this are possible. Vote them up. And internally, I do a lot of this too. I'm not allowed to vote on Jamf Nation myself, but internally, I do push for improvements like this.
Okay, fantastic. Well, that was all of the Q&A we had today. Thanks to William Smith